All right, I hope everyone can hear me okay. All right, so what I'm going to talk about is trying to understand the formation and evolution of the first discovered stellar mass black hole. Um, and really the main thing that we're going to try to understand is the properties of its companion star. All right, so as an overview, I'm going to talk about stellar mass black holes in binary systems, how we go about finding them, why they're interesting, and how they form and evolve. A little bit of the history about Cygnus X-1. And then some of the work that we want to do in terms of understanding the orbit and the orbital evolution of this binary system, and then some of the considerations for the data quality that we'll need to get in order to make some progress, and I'll also talk about why this is a project that's really hard to do with big professional facilities. All right, so there's a couple of speculative approaches to finding black holes in our own Milky Way galaxy that people have suggested, but that it's not clear whether people have made them work successfully yet. Both of these approaches are things that people have made claims about, and the claims are reasonable but not conclusive at the present time. Right, so one of them is by using wobble. So the same kind of approaches that people use to find extrasolar planets, you can also use to find black holes. And you might think it's easier to find the wobble due to a black hole in a binary system than it is to find a planet that way. But black holes are so much rarer than planets that the nearest objects that have black holes in binary systems are going to be a lot further away than the nearest objects that have extrasolar planets. And so you're talking about looking at a much larger number of stars before you find something, and looking at fainter stars. And so the figure on the left illustrates how the Gaia satellite, which is currently collecting data and which will make its next big data release in a couple of weeks, may be able to find black holes from wobble in binary systems. So both wobble on the plane of the sky and radial velocity wobble. Another approach which has a very long heritage, and which is the attempts to use this approach, gravitational microlensing, so far they're still ambiguous about whether they've been successful for the purpose for which they were intended, but they led to a wealth of data on variable stars. And so if you go back to I think it was the late 1980s when the Macho project started, some people thought that the dark matter in the halo of the Milky Way galaxy might be mostly made up of stellar mass black holes. And these are called massive compact halo objects, or machos. And people designed surveys to go and look for them through microlensing. And this is a way that you can find black holes even if they're not in a binary system. If a black hole passes almost perfectly between a background star and us, then what can happen is the rays of light get bent by the gravity of the black hole, and we get more light reaching the Earth than we would get without the black hole there. And gravitational lensing, you can use the equations for geometric lensing as long as you know how to turn a mass into a lens. And it really works on the same principle. You're magnifying the brightness in some directions and demagnifying the brightness in some other directions. And so as a result, if the black hole is moving relative to the background star, you can see the background star get brighter and then fade. And it has a very characteristic signature if it's a microlensing event. The challenge is figuring out exactly where and what mass the lens is. So there are a few examples of things that look like they might be black holes, but there's no conclusive evidence from that approach yet. So what has worked for finding black holes in our own Milky Way galaxy is to look for what we call X-ray binaries. So on the left, I have an image of an all-sky survey of made with the MAXI telescope, which is an instrument on the space station, which scans the whole sky every 90 minutes for new X-ray sources. Over the years that MAXI has been operating, it's built up a good map of the whole sky in X-rays also. This kind of approach, looking for new bright X-ray sources, is really effective for finding black holes. But there are also some of them that are persistently bright in the X-rays. And the reason why black holes can emit X-rays is highlighted here. And if you want to see a bunch of images that look kind of like this of X-ray binaries and cataclysmic variables, and learn how to make your own computer-generated images like this, if you go to Rob Hines's webpage at Louisiana State University, he has a tool and an image gallery, and I took Cygnus X-1 from his image gallery. So what can happen in some cases is you can have a black hole that's in a close binary system with another star. And when this happens, the black hole can capture mass from the other star in two different ways. One is if, like in Cygnus X-1, there's a strong stellar wind from the normal star. Some of that stellar wind will be gravitationally captured. The other possibility is, and this is more relevant for lower mass companion stars, is sometimes the star gets so close that the inner face of the companion star is equally well attracted to the black hole as it is to the center of its own star. So in either case, the capture of that mass can lead to the formation of an accretion disk. And the gas will then spiral in towards the black hole and then eventually cross the event horizon. As it does that, a lot of gravitational energy is released. And half of that gravitational energy goes into heating up the gas that's falling in. Okay, now when you do that, in cataclysmic variable stars, for example, when you heat up that gas as it falls onto a white dwarf, it gets up to the temperatures where it can emit optical and sometimes ultraviolet light. But when you have a very deep gravitational potential well like a black hole or a neutron star, you can get all the way up to temperatures of about 10 million degrees Kelvin, and you can emit strong amounts of X-ray emission. And in some other cases, you can even get up to about 100 million degrees, or sorry, even up to 1 billion degrees Kelvin and emit very high energy X-rays. All right, so then the next question is, how do we confirm that these objects are black holes? And this comes from a couple of different kinds of data analysis that you need to do. Okay, so the first one that you can do is you can make repeated measurements of the radial velocity of the companion star, and you can plot that versus the orbital phase, and you'll get something that usually looks very much like a sinusoid, and then you can measure the period and the amplitude of that sinusoid, and that gives you something, and that's telling you the radial velocity, but you don't know if you have a face-on system where the orbits are really fast, or an edge-on system where the orbits are what they seem to be like. And so the harder part is actually measuring the inclination angle for that binary. This can be, this can be done using what we call ellipsoidal modulations. So when you have a donor star that's very close to a black hole, its shape gets distorted. And at different orbital phases, you'll see a different shape and a different brightness for the donor star. Okay. Now, if you have something that's very face-on, you barely change the shape of the donor star as a function of orbital phase. Whereas if you have something that's edge-on, you see much bigger changes in the brightness. And if it's really edge-on, you can get eclipses. And if you get eclipses, that's great, but we don't have very many eclipsing black hole systems. All right, and so that process is illustrated in the figure on the right. There's a big challenge with doing that ellipsoidal modulation measurement, which is that even in the best cases for most of these binary systems, there's still some optical light from the accretion flow that's diluting the amount of modulation that you get from the ellipsoidal modulations. And so you have to do a lot of hard work to correct for that. And that's illustrated in this paper that Andy Cantrell did about 12 years ago. All right, so now why are we interested in black holes? And there's a couple of main reasons. So in the top figure, I'm showing effects of general relativistic light bending that changes the photon trajectories. And then you can get images like what we've seen from the Event Horizon Telescope for supermassive black holes. And there's a whole bunch of other general relativistic effects that you can test when you start finding black holes in the Milky Way galaxy. All right, so the Event Horizon Telescope, for example, is not very sensitive to the spin of the black hole, whereas X-ray observations of black holes and binaries are very sensitive to the spin. The other thing is that it gives us a way to understand what happens in supernova explosions. And that's illustrated on this plot here, where we show the masses on the x-axis and the number of objects on the y-axis. And then we have the observed objects where the neutron stars are all under about 2.5 solar masses, but the lowest mass black holes that we're really confident are black holes are about 5 solar masses. And so one of the questions is, are there observational biases that have prevented us from finding these objects in here, or is there really a gap? The answer to that question is kind of highlighted, or the implications of the answer to that question are highlighted in the bottom panel. So if we have very rapid explosions of supernovae that produce black holes, then we produce that gap. Whereas if the explosion is delayed relative to the collapse process, then we don't get that gap. Right? And it turns out it's really hard to understand the details of the actual explosion mechanisms of supernovae. So if you look at the supernova light curves, the problem is all you're seeing is how much energy is injected and how massive the envelope is, but you can't tell what's happening on the inside because all the light produced in the inside gets scattered many times before it gets to you. So if you want to understand the explosion mechanisms, you have to either use processes like neutrino measurements or gravitational wave measurements that allow you to see through that envelope, or you need to use some more indirect approaches. Now, neutrinos and gravitational waves sound great, but the problem is that we can only detect supernovae in our own galaxy and maybe the nearest 1 or 2 other galaxies using those techniques. So we're kind of left with indirect methods. And one of the best indirect methods is to look at the properties of the neutron stars and black holes that get left behind in the supernova explosions. Right? And so that's one of the main reasons that we're interested in understanding this, is that understanding the processes that make black holes in binary systems helps us understand the processes that make supernovae. All right, so now I want to show this cartoon that just helps illustrate how complicated it is to understand the binary evolution processes that produce these X-ray binaries. And this is a cartoon that illustrates one particular channel for binary stellar evolution. But depending on the initial properties of the 2 stars in the binary and a whole bunch of other things that can happen along the way, you can get very many different kinds of outcomes, and you'd have to make probably 100 of these cartoons to really describe everything that's going on. But basic idea is you start off with a pair of high mass stars. One of the stars starts to expand off the main sequence and becomes a big star that dumps matter onto its companion star, right? And then you get this Wolf-Rayet star, which is a star that's lost its envelope, but has very strong stellar winds. And you have an inverted mass ratio where the more evolved star, which is the Wolf-Rayet star, is also the lower mass star, right? Then you have some kind of supernova that makes a neutron star or a black hole. And then you have a period of time where you emit X-rays. Now, the donor star starts to expand off of the main sequence. And now the donor star, swallows up the black hole or neutron star. And when it does that, the 2 cores, the black hole and the core of the other star, spiral in together. And that ejects a lot of the envelope of the what was the donor star. And now you have another Wolf-Rayet star. Then you get another supernova explosion or black hole production event. And then you can end up with a pair of compact objects that can spiral in and form gravitational radiation sources. Right, and so this is one of the many possible channels that can happen for binary evolution. And what we're talking about is understanding what's going on at this stage of one of these objects. Cygnus X-1 probably won't turn into a gravitational wave source. Probably when it gets to this stage, instead of having a common envelope, the black hole will just merge into the core of the massive star. But exactly what will happen depends on some things that we don't understand well enough yet. All right, so a project I was excited to be involved in where the paper came out about 2 years ago is this paper by James Miller-Jones, who works at Curtin University in Australia. And there, what we did was we got a bunch of radio measurements for Cygnus X-1, and we were able to see the motion of the radio source across the sky. Now I want to highlight how small these motions are. They go from minus 0.4 to plus 0.4 milliarc seconds. So for those of you who have good sized telescopes on really good sites, you can probably get to within a factor of a few thousand of this image quality. But this is really something that you can only do right now using the best radio telescopes that we have on Earth. All right, and this wobble here is a geometric parallax effect. So this is actually giving us the distance to Cygnus X-1 with really high precision. All right, and now it turned out that the distance was a little bit further away than people had thought before. And because of that, that turned out to push the mass of the black hole up a little bit from what people had thought before too. And it also made the donor star more massive than people had thought. All right, so all of these things end up working together. The black hole mass now turns out to be probably a little bit over 20 solar masses, which is heavier than a lot of people thought was possible from normal binary stellar evolution. And it also leads to a problem that the donor star now, being more massive than we thought it was, should also have a mass loss rate from its stellar winds that were higher than we thought. And that should then lead to the black hole capturing more wind than we thought it should capture. And that should make the X-ray source brighter than it actually is. right? And so this has led to a little bit of a conundrum that we're hoping that we can solve by understanding what the orbit does. Okay, so the thing that we're going to want to do is measure the orbital period derivative of this binary. So see how the orbital period is changing as a function of time. This is something that has been done for a bunch of other high mass X-ray binaries in the past using X-ray monitoring data, but the objects for which this has been made to work in the past are all objects that have eclipses at the X-ray source. And so then it's really easy to measure the orbital period with very high precision. Cygnus X-1 doesn't have eclipses, so we have to use smooth changes in the brightness as a function of the orbital phase in order to figure out what's going on there. Okay, so I apologize for the quality of this figure here. I pulled it out of a paper that didn't use bold enough lines, but hopefully people can at least see the data points, and then I can help highlight what's going on here. So we have a V-band, B-band, and U-band light curves. And these are folded light curves, folded on the orbital period. And I've put the magnitudes close to the tick mark so that you can see the ranges that we're having here. So in the V-band, it goes between about 8.82 and 8.86 for magnitude. In B, 9.63 to 9.67. And then in U, 9.32 to 9.36. Right, and you can see these are pretty close to sinusoidal light curves. These data were collected from 1971 to 1997. And if you want to see this figure in better detail, there's a paper by Catherine Broxop and collaborators from 1999 that gives a summary of this, and that's where I took this figure from. All right, so the orbital period is 5.599829 days, and then this is the uncertainty on the orbital period. So we actually have a very precise measurement of the orbital period. And then this is the ephemeris. So this is where the zero phase is. And again, that's known to 0.009 days. All right, so now the amount of stellar wind that you have from the companion star will determine how the orbital period changes. And the reason for that is that you need to conserve angular momentum. And so the mass loss leads to changes in the orbital period. And pretty good expectation that we have is that the mass loss time derivative of so m dot is the mass loss rate and m is the mass, and that's going to be about 10 to the minus 7 per year. So on time scale of 10 to the 7 years, you would lose the whole mass of the star. And then the period derivative divided by the period should be pretty similar to that. And there's some factors of around 2 that come in that can vary a little bit depending on what assumptions that you make. All right, but what this means is that if we want to measure, so measuring the actual period derivative is basically impossible. We can't measure the period directly to that precision. But what we can do is see if the ephemeris changes from the old values. And so if we can get the ephemeris measured to an accuracy of 45 minutes, or better, significantly better than 45 minutes, then we can go and see if we're seeing a period derivative of about the size that we expect, right? So the actual period change is just going to be a few seconds, and we're not going to go and do that. All right, so now one of the other things that we have to worry about is this is data from May through August of 1996, and the optical data are here, U-band here, B-band here, and then the top 2 panels are showing X-ray data in 2 different bands. And what you can see is that it doesn't show exactly the same profile as the average value that had been obtained from the earlier data. And probably what's going on here is that there's a stellar wind from the donor star, and the stellar wind can sometimes absorb some of the light from the star. And so if the stellar wind is varying, which stellar winds tend to do, then you need a little bit different amount of absorption. And so if you try to make these measurements over too short a time scale, you probably don't make them reliably enough. All right, so some of the challenges why we can't do this with public variability data, and there's a couple of projects that you might think should be able to do this. One is Assassin, which takes images of the whole sky every few days. The problem is that Cygnus X-1 is about 9th magnitude. Assassin saturates at somewhere between 10th and 11th magnitude, depending on exactly how good the seeing and the cloud cover were on a particular night. So Cygnus X-1 is always going to be saturated in Assassin. If you're looking for really strong variability, you can use moderately saturated stars and get useful information out of the assassin data. But we're looking for pretty subtle variability, only about 0.04 magnitudes. And so we don't want to try to backtrack out the saturation effects from assassin. All right, so many of you also, I assume, are familiar with TESS, which is a satellite that looks for extrasolar planets. And it's similar to Kepler in the sense that it stares at a patch of the sky and makes very precise photometric measurements. The problem is that, and unlike Kepler, TESS observes the whole sky, but also unlike Kepler, TESS observes patches at a time. And TESS only observes for 1 month at a time. And since we saw from that stellar wind variability in the previous slide, on a 1 month time scale, that's probably not going to be a reliable measurement of what's going on. We can't trust the TESS data to do this stuff accurately either. Okay, so what else do we want to do? We will ideally also want to use the same filters as in the past work. So UBV, Assassin works in Sloan filters, and TESS is basically a white light filter. So the combination of the need for high precision and a very long data train, and the preference for using U, B, and V rather than these other filters means that we really want to make a dedicated campaign to try to figure out what's going on with the Cygnus X-1 in modern times. So it's been 25 years since the old data were taken, and that's long enough that the ephemeris should have changed, and that gives us a good opportunity here. All right, so some of the technical requirements for the work. So we'd like photometric accuracy for each data point to be about 1% or better, since that peak to trough amplitude is about 4%. Time tagging, accuracy is probably more important than precision. So, you know, if you need to take a 3-minute image to get the data out, as long as we know exactly when you took the data, that should be fine. And then filters, Johnson UBV will make the comparisons easier. It's not strictly necessary, but it'll make the project a lot easier to use the data if people do it in the same 3 filters. And I think it would be nice to get data in all the filters so that we can, that may help figure out what the stellar wind is doing, because the stellar wind absorption will probably be worse in the ultraviolet than the V band. All right, so campaign duration requirements. So ideally, I would say a few data points, with a data point roughly every day. You know, there will be parts of the year when you can't observe this because it's too close to the sun, but for most of the time, get a data point every day. I think that'll probably work. We don't really have good characterization of what the stellar wind variations are doing, so we don't know exactly how much data we need. But the existing data was 800 data points over 26 years, and that gave an accuracy of about 13 minutes for the ephemeris. So my guess is that if we get 1,000 data points or so over a few years, that'll probably work. And probably the number of data points is more important than the full-time baseline. So this is something where we'll have to do a little bit of experimenting to see if a few years is really enough data, or if a campaign needs to go on longer than that, but that'd be my guess. All right, and that's what I had to say to you all, and I wanted to leave plenty of time for questions from the audience and comments about how easy it is to get this kind of stuff done with the kind of equipment you all have. So I'd be happy to take questions. Now, one thing is, I was really having a hard time hearing Bob when he was giving the introductory remarks. So if people could either type the questions into the chat or relay them to somebody who's standing next to the computer that's running the Zoom, that would help a lot. And do you want me to call on people with questions, or is somebody moderating the session?
Wait, Tom, can you hear me now?
Yes, I can. Yeah.
Okay. Ladies and gentlemen.
And I saw there was Jessica Draper had a hand raised in the online.
Did you get that, Tom?
I didn't hear anything. I saw somebody standing like they were probably asking a question, but I didn't hear anything.
On the potential utility of polarization measurements.
People have done polarization measurements, but There's some ways that you can try to use polarization to understand the inclination angle, but it's a really messy process. I think it would be interesting to see polarization monitoring of Cygnus X-1 and some of the other bright X-ray binaries. I think if you wanted to do polarization on an X-ray binary, I think it might be more interesting to try to do it on Scorpio X-1, which is also very bright in the optical, because in Scorpio X-1, the optical emission is mostly coming from the accretion disk rather than from the companion star. And if somebody wants to send me an email afterwards with more to think about for that, I'm happy to go through that. But for this particular project I was discussing, I haven't thought about how polarization would help, and I don't think it probably would, but it could still be interesting to do for other reasons.
Follow up on that, Eric?
I guess I was also wondering about the ability of serendipitous polarization surveys.
Could you repeat that? I barely heard it.
Also wondering about the possible usefulness of serendipitous polarization surveys as discovery tools, I guess black hole binaries.
Oh, I don't think that would be very helpful, because the polarization from the X-ray binaries is usually very weak. And so I don't think that would be a very effective way to look for them. The variability of the, and also because you can have interstellar scattering creating polarization, you really, only the variability of the polarization is easy to use in the optical band.
You got that, Eric? Thank you. Okay, here's Woody Sims.
Hi, Tom. A question about the 10 mass loss rate of donor star. How long a time period is it? Linear, or does that have a curve to it?
Okay, again, I was hearing sound but not making out what you're saying.
I must have the magic voice. The question was regarding the 10 to the minus 7 p dot over p.
Yeah.
Is that actually linear, or over the long haul, is there a curvature to that?
It's probably neither. So in terms of what happens, okay. So in humanly accessible timescales, it's probably pretty close to linear. It's driven by conservation of angular momentum and what the mass loss rate is due to the stellar winds. So on short time scales, like tens of years, the stellar wind may vary sporadically so that you don't get a perfect measurement, but the kind of the average value, if you took a bunch of 10-year segments, is probably going to be the same. Now, as you go to hundreds of thousands of years, as the star's bulk properties really start to change, then you could get a real change in the mass loss rate and therefore the period derivative.
Got it. Thank you. Okay, John, can we unmute Jessica for her question?
Hello. I was wondering if you could go back to the slide that has the schematic of the compact object evolution.
The cartoon?
Yeah.
Okay, yeah.
So when we get to, I guess it'd be 1, 2, 3, the fourth step there where you have the supernova of the first massive object. What, would that not have a shockwave or something that sends the other star away before you can have this pair of compact objects?
So yeah, the blast wave will hit the companion star. And people are trying to find observational evidence for the blast wave hitting the companion star, but it shouldn't do too much because not that big a fraction of the blast wave runs through the companion star. So the biggest problem for keeping these binaries bound is actually just that if you lose a whole bunch of mass all at once, like if you lose more than half of the mass in the binary, that should make it become unbound. And the other issue is that probably in some cases, the explosions are asymmetric. And if you have an asymmetric explosion, you may end up unbinding the binary and giving a big kick velocity to the compact object, the black hole or the neutron star. So like if we look at pulsars, some of them are moving across the sky at 1,000 kilometers per second. So they almost had to have been born in asymmetric explosions. So definitely this is a potential failure point where the binary can become unbound, but it's probably not going to be too important in terms of the blast wave blowing the companion star away. The companion star is a lot heavier than the blast wave, and only a small fraction of the blast wave actually hits the companion star. One thing that may happen is you may pollute the atmosphere of the companion star, and there's a few cases where if we look at the chemical elements in the companion stars, they're a weird set of elements that suggest that there was some pollution there.
You happy, Jessica? Okay, I'll assume so. Mr. Green.
Hi, Tom. This is Wayne Green. In IAER3 data that's coming down, are we going to be able to see from the tags that are going to be in those data signatures that are indicative of these stars?
Okay, could somebody repeat that, please?
Okay. IAER3 data.
Yeah.
With spectroscopy.
Yeah.
Same company with the Canon is going to be looking for metallicity ratios. Is it possible metallicity signatures for these types of events or maybe pending events?
So for hot stars like the donor star and Cygnus X-1, I don't think they'll do very much useful work because the spectroscopy window for Gaia is a very narrow range of wavelengths, so they're not sensitive to a lot of elements, and the elements that they are sensitive to, I think, tend to be fully ionized in really hot stars. But I haven't looked at that carefully. It might turn out to be interesting, but it's not obvious to me that it will.
Here's John Hoot.
From a practical point of view and getting more people involved, if people are using one-shot color CMOS and transforming at least the B and the B for you, is that going to give you enough more information to be useful?
Yeah, I think that would certainly be helpful. We'd have to check on how good the transformations are also and see what uncertainty that induces. But since we know the color of this star very well, I think that should be something that can be done more precisely than for cases where you don't know the colors ahead of time. So I think that could be very useful, and yeah, I'd definitely like to see it if people could do that.
Yeah, and John's pointing out with the three-color chip, you get B and V at the same time at the same air mass, which sounds good.
Yeah.
And if I remember from your magnitude chart, this is not a strongly colored star.
That's right. It's close to 0 for the colors.
Okay.
It's actually negative color. Where is it? Here. Yeah, it's actually a negative color between U and B, and then 0.8 between B and B.
That sounds good. And so anybody who is doing exoplanet transits should be able to easily meet your accuracy requirement.
Yeah.
What about spectroscopy? I think some of our spectroscopists might be able to do radial velocity on this guy.
Yeah, that's an interesting question. So certainly, if people can get accurate spectroscopy, that would help. I haven't thought carefully enough about. So if somebody is interested in looking into that, it would be great if they sent me an email afterwards, and I can look into that. This is a blue supergiant, and blue supergiant radial velocities are sometimes a bit messier than other kinds of stars, but I think it's probably possible. Because I think some of the people with really good equipment can even go to 10 or 11, right?
Yeah, although not with high accuracy in the RV.
Okay. What do you consider high?
lower resolution spectrum we can get there. I think the high resolution that we might, but the only way to find out for sure is to try.
Yeah. And I don't remember off the top of my head what the radial velocity amplitude is here. It's a lot lower than for other X-ray binaries because it's a longer orbital period, and because here the donor star is the heavy star, and it's kind of face on also. So all of those things work against you, but it is really bright. So if somebody's interested in that, we can definitely discuss it. And that you can probably also get by with a little bit. You can probably get by with shorter data trains for that. Because you don't have to worry about the stellar wind messing up the radial velocities in the same way that it messes up the photometry. So that might be an interesting approach.
What delta magnitude do you see from that changing stellar wind signal? Do you know off the top of your head?
Yeah, so this plot here is in Stefanski's. And so what it really is that it messes up the whole light curve. And it looks like, what is this, 20 over 300? So it's a little bit less than 1%, but it's not following the shape it's supposed to, which is the bigger concern, that you just get random variations of a percent or so.
So all the more reason to monitor over several periods to try to average that out.
Exactly, yeah.
We have another online comment or question? Anybody else in the room? One more? Oh, yeah, he was pointing here. This is Milijansky's, but 335 divided by, or say minus 305. So that's 20.
Oh, I divided wrong in my head, didn't I? Yeah, I was off by a factor of 10. So yeah, it's about 20 over 300. So that's 2 over 30. So that's actually 0.06 magnitudes of variation here. So it is substantial on the short time scales.
Okay, so we absolutely need to average over periods in order to detect actual ellipticity.
Yeah.
Well, that's scary. I think my student Matt Wilson might have detected this instead of the ellipticity. Any other? But yes, Calais talk.
Hi. Is there anything that can be, so you mentioned earlier that the gap between the neutron stars and 5 stellar mass black holes is kind of being probed to find out about the explosion. Is there anything that can be found out about the original explosion from like this single dot measurement or period measurement?
No, this single measurement is going to tell us more about what the status of the donor star is right now. And this black hole is actually off the chart to high end in terms of the mass compared to the rest of these data. So in this case, we think matter has been sloshing back and forth between the 2 stars in this system. And then also that the stellar winds in the system may be weaker than theory work has suggested in the past.
And follow up to that, when will you know, like how long, what test would tell you when the data begin to be useful from this campaign?
The way I would do it is I would take blocks of several months and see how well the answers agree with one another. And if the answers are jumping around at the level that we care about, then I would say that we need to keep going longer. Whereas if everything's stable, then I would probably want to go longer for just a little bit more just to make sure. But that's when I would start to trust it.
Anyone else? Looks like not. Thank you very much, Tom, for doing this. For those of you in the room, I'm going to put a sign-up sheet on the table in back. So if you're interested in pursuing this project, put your name and email on there, and we'll have a Zoom session to sort out details like what comp stars are we going to use and things like that to try to get an initial look at this system, compare our data, learn where we messed up, and then start considering the results.
So if you read the Broxot paper I mentioned, and and then go back to the original set of data. They use the same comparison star every time, and that's listed in the paper. It has a BD number that I don't remember, but there's a single comparison star that's always been used. So that would be I would think, the one to continue using.
Yep, that's our target then. Cool. Thank you very much, Tom. You're welcome to stick around or go off to your staff meeting, whichever fits your schedule best.
Okay, thank you very much. I have a collaboration meeting coming up soon. I do have to, but I'd be very grateful if any of you all get excited about this and want to join, and feel free to look me up and contact me by email if you need to. All right, bye.
Thank you very much.